Hi, organic chemistry students. Today we're going to talk about conformations of alkanes and then how to draw their energy diagrams. We're going to start off with actually ethane. Let's not jump right into butane. Let's start with ethane. So I'm going to make a model of ethane and show you what we're talking about in terms of conformations. So staggered ethane is preferred. How do we look at it? Well, when we're looking at ethane, we want to look down the central carbon-carbon bond. And what happens is with single bonds, there's free rotation about that single bond. And so for ethane, this would be completely eclipsed where the hydrogens are lining up versus staggered is when those hydrogens are in a window. Now, we've all been asked to stand in a window before. Maybe in a group photo, a photographer asked you to stand in the window of the two people in front of you so everyone would be able to see your face. Maybe you're in choir and your director might ask you to stand in the window of the two people in front of you. That term is just meant to be like stand in that space. Well, here, these hydrogens are in the window, and that's far preferred, just like your choir director prefers it and that photographer prefers it. Maybe you're a dancer and you've had a window spot where you need to be between two other dancers, or a cheerleader might have a window spot between two other cheerleaders so that the audience can see them. Well, this is preferred. This staggered or window, if you will, idea is really preferred for the alkanes, and that'll be a lower energy conformation. And then we have to add in potential energy to reach that eclipsed conformation. And this adding in of energy is called torsional strain. And then there's less torsional strain right here. And I think of torsion as twisting. And that's how I remember that this torsional strain that's added, this added strain is due to that twisting into that eclipsed conformation. It doesn't want to be eclipsed. It would prefer to be staggered. So let's move on to butane with 4 carbons. And if we take a look at butane, I just want to show you the carbon chain with 4 carbons there. And I've got all the hydrogens on there. With butane, we want to stare down the central CC bond. So here's some carbon-carbon bonds. We're going to look down this central carbon-carbon bond. And so in our Newman projection, and we've got Newman projections over here, in our Newman projection, this spot right here in the center, we can mark it with a dot. This spot right here, it represents 2 carbons. So in each of these Newman projections, it's 1 carbon, and then there's supposed to be another carbon right behind there. You can't really see it, but that's the idea, is that this point right here represents 2 carbons. So I'm going to start to line up butane the way that we see it in other models. But this would be really staggered. And then if we keep moving it around, again, we can rotate about that central CC bond. And where we're starting with this online model is with the syn conformation. So up here where everything is eclipsed. So we've got all this eclipsing of those methyl groups in this syn eclipsed conformation. And so I've drawn that example here for you. Let me just erase. I've drawn that example here for you where I've put in these 2 methyl groups. And notice here they don't look like they're right on top of each other. You can imagine if they drew the second line right behind the first line, we wouldn't be able to see that it's there. And so even for our eclipsing, it looks off a little bit to the left, but the idea is, okay, here is my eclipsed conformation. If I had it lined up perfectly, you couldn't even see what was behind it. And so instead, here's that carbon that's behind. I'm trying to show it a little bit, but it's really hard to get the angle just right. Instead, there's that carbon that's a little bit behind. So instead of showing it to you totally like this, it's just moved a tish like that. Then we want to try at 60 degrees what happens. Okay, so if we look over here at the molecular model at 60 degrees, okay, well, I can see the 4 carbons. They line back up again. At 60 degrees, we're just going to rotate. And the way it looks on these Newman projections is it looks like the carbon in the back is rotating. The carbon in the front looks fixed. Look how it's really unchanging, the way that the Newman projections are drawn. This methyl is fixed. So I'm going to fix that methyl right here. And then I'm going to just move the methyl in the back to that window to match up with the model that I'm looking at online. Okay, so when I do that, it's off in this window on my right. So my pen here is particularly suited for this spot. But here, my methyl goes right here in this spot. That means that out in front are these 2 hydrogens down here. So I've got to draw those 2 hydrogens here and here. And then I've got a hydrogen that is down in the back right here. So I better put that hydrogen. And then I've got, hard for me to show it. I've got a hydrogen that's down in the back. And then I've got one more hydrogen right here in this window. So here's this hydrogen in the back. So what's peeking out from behind in these Newman projections are these hydrogens in the back. One down, one right here. Here's my 2 in the front. So 2 hydrogens in the front. Here's my 2 hydrogens in the back. There's my methyl popping up in the back, and I've got this methyl in the front. And then I'm just going to keep rotating. And so I can do that with my molecular models online. That's what you'd be doing, is looking through these and be going, okay, well, at 120 degrees, we eclipse some. And that eclipsing is not the worst eclipsing there ever was. It's not as bad as where we started, right? But it's not great because this hydrogen is eclipsed with this methyl. And then we come down into this window and it's finally like, whew, what a relief, right? Like now we are really what we call fully staggered, and that's called the anti-conformation. And look how that looks like a regular zigzag carbon chain, because that's what the molecule wants to be. That's why we draw hydrocarbons normally zigzag, is because that's the lowest energy conformation of those hydrocarbons. And then we're going to eclipse a little bit. And so we're going to move 60 more degrees here. We're going to eclipse a little bit, 60 more degrees. And then we're going to go to gauche. So notice how these staggereds have fancy names like gauche for that, staggered. And then we'll move to this fully eclipsed conformation. That's called sin. So this fully eclipsed conformation was called sin. This fully staggered one was called anti. These eclipsed guys don't really have names. These are just referred to as gauche right there. But these eclipsed ones don't get their own name. And here we've got, let's just start over again. So let's start over again. I was going to say here we got sin. So let's just look at the whole rotation again, starting at sin. We're going to go to gauche. A little bit staggered, a little bit better. Let's go to eclipsed. Those eclipsed don't have any fancy name. We'll go to anti. Then we'll go to a little bit eclipsed. Then we'll go to gauche. Trying to get the angle a little bit better so that you can see it. There we go. I think the angle is a little bit better on that gauche. And then we'll go to sin. So if I just hold my model and focus on it for you, and I try to rotate them without blocking your view of it. Again, here's sin, here's 0 degrees, and then we're just going to rotate 60 degrees at a time. There's the first 60, 120, 180. The trick is I have to switch. 180, 240, 300, and then we're going to be totally eclipsed here again, 360. So hopefully this has given you a better understanding of how butane has so many different conformations. And now I just want you to fill in the remainder of this virtual modeling lab sheet.